You guys are hearing me though. I'm assuming. Jared, okay, Jared's there. Okay, well, I'm going to cover things that are related to the homework, obviously, and we're going to see that things are going to get a lot less mathematical in the short term. It's going to be systems modeling concepts though, so it's pretty fun material and pretty useful material as well. So I had a confusion early this morning where when I was updating the hints, I was updating them as set number 11 because I was just thinking ahead, but then I fixed all of that later. So I did update the hints for set number 10. I finally posted the set number 9 solutions. Of course, last week I posted 2 old exams, and we'll be looking at those on Thursday. And I probably will have the project pretty much ready to go by Thursday, maybe even talk about it some on Thursday. It kind of depends on how I want to deal this out. The last official chapter of notes that I plan to go through is the Appendix A, which is a much different flavor from what we've been doing right now, whereas the Project 2 is going to be jumping mostly into digital communications, doing some things that we've already done in sort of a lab setting. And just remember, again, that Project 2 is not really writing very much software. It's just doing experiments, capturing results, and then drawing conclusions from the results. So I'm going to move over to where we left off. We had looked at some simulations. I did not look at this old MATLAB simulation in the bandpass domain. Instead, I've replaced it with a complex baseband simulation, which is far more useful the way I do things today. So what I want to do is jump over and spend some more time looking at that, and at the same time we'll pick up problem number 2 on the homework. So just quickly looking at the homework sheet, and then this is the one that I pushed up to Slack and on the website that has the handwritten notes in here as well. We'll come back and take a quick look at problem number 1, the first and the easier of the phase lock loop synthesizer block diagrams. We'll look at a more exotic one in the notes as well as this simple one. But I want to right now spend some time on problem number 2, which even though I posted up another page today, I still didn't get it totally the way I'd like to have it after I was studying my solution. So let's just go in and take a look at this. And we're going to take a look at it in Python and then come back over and look at this some more. So I did repost the notebook for chapter 4. The biggest feature that I added to it was this figure. So that's when you unpack the zip, there is a PNG file in there, which is this graphic, which could possibly get lost if you didn't keep it with the notebook. So just make sure you move it to wherever you put the notebook. And this is the model for a phase lock loop at RF, so to speak, and modeling everything in terms of a complex baseband signal, so we can still keep the center frequency at 0 hertz, which would be nominally the carrier frequency. And the sampling rate doesn't have to be ridiculously high like it would be if we tried to do a full bandpass domain phase lock loop. We'd want to be able to simulate what's going on inside the control portion of the loop, but the problem is we'd have to sample at greater than twice the highest frequency, which would be essentially greater than the carrier frequency, and that would just make things very, very slow. So the complex baseband loop is definitely the way to go. And it's also very relevant for digital signal processing and software-defined radio types of applications. So in this loop, as I say here, nominally the carrier is 0, but you can freely move the signal around, up and down, by putting in a carrier frequency, and you'd be moving it up or down because it's a complex sinusoid that has phase modulation added onto it. So it has a lot of nice features. It's very much like a real phase lock loop would be in the analog domain, and definitely like a phase lock loop you could be dealing with in a software-defined radio. So the main things that it allows us to do is that we have a phase detector, which in this case is a complex multiply, and when we multiply the e to the j theta hat of t, its conjugate will be e to the minus j theta hat, and then that comes and multiplies this signal by that e to the minus j theta hat, and we end up with e to the j theta of t minus theta hat of t nominally. And if there is a small carrier offset, FC, we'll pick up that frequency difference as well. But then if we take the imaginary part of that, that's like essentially forming the sine of the phase error. So we'll have, suppose FC is 0, we'll have theta of t minus theta hat of t, and we'll have the sine of that because that's what the imaginary part will be. And now it really looks like the phase lock loop that we've been dealing with for the past few class meetings. And that's why I call that E sub d of t, and I think in my notes that I wrote out, I wrote a little bit more detail on there too. Make sure I know what I'm talking about and I haven't just said something that wasn't true. Yeah. What I did over here in the handwritten stuff, I took it right out of the Jupyter Notebook, and I said that that is effectively AC times the sine of psi, which would be our phase error that we've talked about in the past. So that's pretty handy, and is why I'm also having you use this as the simulation foundation for this problem number 2. So we have the phase error, which is the sine of the phase difference. We have a loop gain K. We have a loop filter we can put in. We have an integrator from the VCO, and then the phase output theta hat drives a complex sinusoid, and then that comes back around and forms the error signal. So the components that we can freely deal with are in the red, K, Fs, and 1 over S. If I was doing this as a software-defined radio model, I would use the Z domain, and I would actually use discrete time signal processing type notation. And that's what the phase lock loops class is doing right now. But early in the semester, they started with the complex baseband phase lock loop modeled in terms of the S domain. So that's the one we're using here. The integrator is a numerical approximation to an integrator, and then the loop filter is the same idea. If the loop filter happens to have poles and zeros in it, those are modeled with numerical approximations as well. I can't really go scribble on that, but I think I'd like to explain that to you a little bit too. So I'm going to do that right down here to explain to you how a loop filter would work in a continuous time model. If we have our second order loop model, we have S plus A over S, essentially. And then if we write that out, it's 1 plus A over S. So in terms of our loop filter, the way we could represent this loop filter, actually we can do it like that if you want to. We actually have a block like that, and then we have a gain block A, and then we have another integral. So that's what our loop filter model looks like in the simulation model inside the synchronization module of Scikit DSP-COM. It's an integrator, again, using a trapezoidal numerical integration approximation, and then it's two gain constants, 1, and then A is on the path that goes through the integration, and that's how that loop filter can get built up if we're going to do a second-order phase lock loop. If it's a first-order phase lock loop, this is just a direct pass-through connection, and then there's only the loop gain K. So what I ask you to do in the problem, using this model, what I'm asking you to do is, starting with a complex baseband model, I want you to put in frequency modulation, and I've already got that sketched out in the notebook. I want you to set the first order, in part A, the first order phase lock loops natural frequency to 10 Hertz. Going to set the VCO gain to 1, which just makes things very convenient in the rest of the model. I'm not going to shift the carrier frequency DF, which is the offset that I talk about in the model over here. The DF is way down inside of here. DF is equal to 0. That would allow you to put in a frequency step if you wanted to. That would be right here in this F naught. The F naught would be a DF frequency step that you could turn on, and we could play around with that if you wanted to, but for the standpoint of homework problem number 2, that's going to be set equal to 0. And the frequency deviation constant is 1 Hertz per volt, and FM is going to vary, so all of that kind of works out very nicely too, and that's I've written out in the hints pages. And what I want you to do is take experimental data and compare that to the ideal first order loop filter model versus frequency. So you're going to be taking measurements as if you were sitting in the lab with a function generator, applying a sinusoidal signal to the FM input of a function generator, like in the COM lab in particular, and then you would be using the oscilloscope to take measurements at the output of the phase lock loop. So you would be, not at the output, but at the VCO control point. So you'd be taking, get myself back over here, you'd be taking measurements here of E of t, and you'd want to see what that control voltage looks like as you change the frequency of the sinusoidal modulation, which is entering over at the input as theta through the waveform theta of t. And then you repeat that again for a second order loop that has the same natural frequency, 10 Hertz, but now it's a second order loop with a damping factor of 0.707. And you're going to do the exact same thing. Part A has kind of already been sketched out in the notes. Part B, the idea is you want to get the control voltage, and that is going to be S times the output phase divided by KV. But with KV equal to 1, that is equal to 1. And then theta of S is going to be M of S, the Laplace transform of the message divided by S. So you can see if you just carry this on through, you're going to get you're just going to get M of S times theta of S. And for the case of the first order loop, that is going to work itself out for the case of the sinusoidal input. My pen is sort of dying right here. You're going to get that, and I sketched through that over here in the hints page by telling you that ultimately what happens is that the error control, the VCO control voltage signal is this, like I just said, but the constants are chosen to be such that they cancel themselves out. Kf is 2 pi times Fd, Kv is equal to 1, and the 2 pi is also going to cancel out when you integrate the frequency modulation into a phase, you're going to pull out a 2 pi times FM. So all of these things just sort of go away very conveniently, and you're going to end up with, and assuming that AM here, the amplitude of the underlying FM message is 1. That is 1. Magnitude of that complex e to the j phi, that ends up being 1. So you end up with, like I was saying before, you're going to end up with just h of j 2 pi f. In other words, h of s with s replaced by j 2 pi f. So you're going to be sweeping out the phase response, the magnitude response of the closed loop transfer function. And a note that I added in here is that I prefer the amplitude be in dB, and then furthermore, I've decided the frequency axis should be log. Log base 10 of f. And if you carry this on down to more of the scribbling that I did over here, and we're going to look at the Python section, and that's what this second to the last page is. Here's looking at the Python code. We'll drill into this, but then today I said I want this as your plot. So you're going to have a theoretical curve, which is the black curve, and for the first order loop, it's just a first order low pass filter. And then I want this to be log base 10 of f. So this is like a Bode plot then. And I think I was looking in my plot and my solutions, which are on my other computer right now. And what did I do for my plot? Since I'm going to scratch some things off here. I started at 10 to the minus 1, and I stopped at 10 to the 3. So I went from 0.1 hertz to 1000 hertz. And you can set that up in Python quite nicely, quite readily. This is for the first order. The red dots are the experimental points, and I'm going to show you how you get those in the notebook in a second. The black is the theoretical frequency response for the first order loop. And then for the theoretical, for the second curve, it's going to be the same type of curve, but it's going to do something a little bit different. It's going to have some peaking in it, and then it's going to drop off. So you're going to get experimental data for that one too. And like I say, right up here in the first order loop case, the gain slope corresponds to a first order loop, and then the question is what is going to be the gain slope when you have the second order loop. Once you look at h of s, though, you'll know what you should be seeing, and that's up here in the real hints that I typed out. Let's see. Let's see, where did I put those? I put them somewhere. Oh, they're in the notebook. Yeah, they're right. They're right in here in the notebook, but I'm going to go look at them in the notebook. But they'll be easier to see than they are right here. Actually, they're right here in the notebook. So let's just take the first order loop case, though, and I have that one pretty much started. So I'm going to run the simulation for the first order loop, which means I've got this third argument equal to 1, and if I do Shift Tab, I'll see that that is the loop type, and if it's 1, it's the first order loop. So that's the first order loop. I'm going to set the next argument equal to kV, which I'm going to let that be equal to 1, and then Fn is 10 Hertz, and the damping is 0.707. And it is the nonlinear loop, which, well, yeah, it's a nonlinear loop no matter how you do it. There's no switch for that. It is what it is. It's a nonlinear loop. So then the input signal is a carrier at 0, which is the F0. That's set equal to 0 up above here, because they have dF equal to 0, so F0 is 0. And then the phase modulation comes in as phi of t, but in this case the phi of t is Fd over Fm times Am, and that resolves itself out to be 1. And then you have cosine 2 pi Fmt, so that's the phase modulation that's going in the complex baseband carrier. The loop tracks that. And I'm putting it in with Fm of 1 Hertz over here. So I plot, in the first plot I do here, I'm applying the control voltage EV, and I'll just run this. So there's my output. It's a 1 Hertz sinusoid. So it's tracking the frequency modulation, and because of the way the gain constants are set up, the peak amplitude is 1. I've done a little tweaking on here so that I'm not seeing all of the transients, so I'm starting 20,000 samples from the end, so I don't see the transient. That's what this business is right here. If I just wanted to plot the whole thing, I would just see the whole thing, but you can see here I'm starting at 0.5 seconds, so I've skipped over the transients. So if I was just to do plot t, comma EV, I would see this transient that you see in here. That's just as the loop is pulling in and starting to do its tracking. But for taking measurements experimentally, you want to avoid the transient, and I talk about that in the handwritten notes. You want to start a ways in, and then you want to get effectively the RMS value of this. So to get the RMS value of that sinusoid, I go down here and I compute the standard deviation using the STD function in NumPy, and that's going to be the RMS value. So what is the RMS value of a sinusoid? If it's got an amplitude of 1, the RMS value is what? I'll give you 2 guesses, and one of them is obviously not right. Is it the square root of 2 or 1 over the square root of 2? You can type to me in Slack if you want to. It's 1 over the square root of 2, right? Because we're taking the amplitude squared, dividing it by 2, and then we take the square root of that to get the root mean square value. So I scale the RMS value by square root of 2 so that it comes out unity, and then I go ahead and take 20 log base 10 of that amplitude, so I get the value in dB. And it should come out to 0 dB. It comes out to minus 4/100ths of a dB. But just above here, in the cell up above, I've done a few of the theoretical parts to plotting the theoretical curve. I've taken the closed loop transfer function for the first order loop, which is of this general form. It's kt over s plus kt, but I've replaced kt, I replace s by j2 pi f, actually. I left that off here. It should say 1j times 2 pi. And then I've replaced kt by its radian per second value, which is 2 pi times fn. Plug that in, and then it reduces to this, so I just evaluate it directly. This is the magnitude then when I take the absolute value. And so this is an array of frequency values that this is a quickie little calculation. I would do more points for this to plot your theoretical curve, and then let's just check a point here. This would be at 4 Hertz, right? So 0, 1, 2, 3, 4. So at 4 hertz, my sinusoid should start to decay a little bit. So let's put in 4 hertz and see if I get around 0.92. So I'll change FM over here to 4. And I can see what my amplitude is right here. And it's 0.9289. So it's pretty much what I was expecting it to be. I think I'm just, well, I've got 2 plots. I've got the phasor, but it's the upper plot that we're looking at. So we're seeing it starting to shrink. And of course, if I was to put in 10 hertz for FM, I should be at the cutoff frequency of my low-pass filter, which means I should be at 0.707, which would be this, theoretically, that's this number right here. So what you're doing in this experiment is you're taking the linear response of the loop, getting that response, that low-pass response in dB versus log frequency, and then you're going to take some data points around on the curve, kind of like my picture shows. And then you're going to repeat that for the second order loop. The measurement setup for the second order loop is identical. You just flip the switch in the software, and all you're going to do is let this be a 2. And just to check again, the third argument is the loop type, and 2 is going to make the loop filter look like this, 1 plus S tau 2 over S tau 1. That's just another notation. And when you go ahead and run that, in this case you get a value bigger than 1, and that's because I've already kind of hinted that you're going to be seeing that you're going to have some overshoot in this response. At any rate, the same calculations carry out here. To get the theoretical response plot for this loop, though, you'll have to take this closed loop transfer function for the second order loop, which looks like this, and then you'll have to make some substitutions. You'll again replace omega n by 2 pi fn, still 10 hertz, times 2 pi. A and kt get written in terms of omega n, which is related to fn and damping. And those equations are in the notes, so if you're wondering, and then where those at, we'll go jump and look at them. But this you can plot, you can take this expression here and set it up just like I did in here, make the substitutions directly, plug the constants in, and then replace S by J2 pi F everywhere, and then you'll be able to sweep this guy's response out theoretically as well. Just go look over at the notes again and go back to where I came up with the second order expressions. Here they are right here. So KT for the second order phase lock loop is 2 zeta times omega n. This is actually the numbers right here already worked out for you, and A is omega n over 2 zeta, 44.43, because this was done for Fn equals 10 hertz. You just got to put the theoretical response together. So on the first one, the theoretical part's done. You just need to clean it up a bit so you can plot more points, and then you're going to plot your data points over the top of it. And then you're going to do the same thing for the second order loop. What's a good way to do that? Well, let me just carry on a little bit further. Use this kind of as the jumping off point. So I might, because I know Colton, you'll probably be asking me this later, and this way I can head you off at the pass and say, look, it's not as hard as you think it is. It's actually pretty easy. So let's just take the theoretical data. I've been there before, right? And you've been there before. So we've got the frequency data in F. So I want that to be log base 10 of F, right? And I'm going to have to omit a data point. So let's do something different up here. Let's kind of clean this up a bit. Instead of doing this, make this more professional-like. I'll do f equals log space, which you might remember from MATLAB. So here I get to put in the powers that I want to start at. So let's make this be -1, and we want to go up to 3, and then let's put 200 points per. So this will give us the log spacing that we're looking for right from the get-go. That's going to give me a big, huge, honking data table, so I'm going to temporarily comment that out so I don't have to look at the data. But now I can go ahead and plot it, and now I can actually just go ahead and do a semi-log plot, where I'm going to be taking the frequency values and put those in as the first argument. And then the second argument is going to be 20 times log 10 of this ABS that I had over here already figured out, so I can just literally drop that right in there. Oh, I'm messing up my keyboard because I'm getting confused with my Macintosh keyboard. You guys that work on two different computers don't know what it's all about, but if you only used a PC all your life, you'd be confused for a little while because the keyboards are a little bit different. Okay. Oops. I have to put in here which axis I want semi-log, so semi-log X. And there it is. I'll put a grid on that just so I can make more sense out of it. Look good? It's a first order low pass filter. So then what you'd want to do is just start putting in some of your experimental data. So what I generally do is I'll put them in as lists, and then I'll use red dots. So we already captured some data at 0 hertz. We were at -0.04, if you remember right. And then the second data point we collected, which was right down here, was 0.9289. So drop that guy in, 0.9289, and that was at 4 hertz. And I want to have this in dB, so I'll fix that in a second. Oh, never mind. This has the 0.04 was in dB already, so I have to put this one in dB. So I'll just do it this way. This is kind of kludgy, but I want to put this in dB. Actually, I think I ran that number out down here, but I've got the wrong loop plugged in here right now. Yeah, so that's with peaking, so I have to change the simulation back to the first order loop with 4 hertz. And then run this out, and that's minus 0.64 dB. So that'll let me put that in here directly. And 0, let's see, what did I do wrong here? I didn't have 0 hertz, I had 1 hertz for the first one. There we go. Okay, so I've got 2 data points on here so far. You might run one at a lower frequency still, but then you can see how we're starting to fill out the curve. You don't need to have 100 data points, maybe 10 data points is about it, and you can collect them pretty fast. So what I would do is every time I run the code here and then convert it to dB, I'll just kind of automate this a little bit, and then every time I get a new data point, I just start entering a new frequency value in that list and a new dB gain value in that list, And then the last time I run it, I will have a nice curve. I'll put some labels on the axes and so on and so forth. Look good? Colton, you're the one that generally asks questions on this sort of thing, so does this look fairly straightforward? Yeah, well, it's here, it's captured on video, so you can go back and look at the video. No, I'm trying to get it out here the first time. It's the pattern, I figured out the pattern, so now I'm trying to No, I'm just trying to second guess you before you fire the question. So I'm going to move on from here unless you've got questions on this right now. And I don't know who all is on because I haven't gone to check. It looks like we got everybody here now. So there's a few little things you got to figure out, but it's not too bad. So you're learning how to do Bode plot in a sense in the S domain, which you've kind of had to do already in other instances, I believe, and then put some experimental data points over it. The reason why they're experimental is because you're running this on a loop that is a nonlinear control system, and you just can't easily set up a system to sweep the frequency response. You could, but I don't want you to get that complicated. I'd like you to just get a few points, and it'll fill out nicely, and then you'll have confidence that the second order loop also is following, when it's tracking properly, the expected response based on a linear feedback model. Again, the loop is not strictly linear, but since we're not getting close to pushing it out of lock with the modulation, it is acting as a linear loop, and that's what we're seeing here. We have a transient when it pulls in, but then once we get into steady state, we have a nice measurement like that. And if you were in the lab, you might put your AC voltmeter on this signal rather than the oscilloscope, but the oscilloscopes that you use in the lab have those nice measurement tools on them, right? So you can ask it to give you the peak amplitude, the peak to peak, the RMS, all those other side calculations. So we're doing some of that down here in this fashion. And I know, John, you asked me this question over the weekend, but you could actually automate this whole process. You could cut out a lot of this plotting. You could put a loop around this whole thing and just give it a list of frequencies you want to step over, and then every time it gets done running the simulation, it runs a piece of code here and then puts these numbers into another list, and then you could plot the list versus the frequency list for FM that you started with, and you could automate it if you wanted to. But I'm kind of an artist in the sense that I will take some data and then I'll say, oh, it might be nice if I had another data right here where there's more of an inflection point, so maybe I'll take a closer in data point or something like that. Just see if it's landing okay. That's it for that. And I'm now going to kind of slide down here to get ready to talk about interference and then make our way further down the pathway with this topic. So the next topic here is general loop transfer function and steady state error. So we go back to the original closed loop transfer function for the linear loop, and we put in what the expression is. It's the loop gain KT, the loop filter Fs, and then we also write out what the loop error function is 1 minus h of s, and this is the two fundamental closed loop equations for the phase lock loop, the transfer function h of s for the closed loop, and then the loop error function g of s. So if we were using a phase lock loop like they're used in SATCOM a lot, you've got a platform that's flying up in space, and that platform is in motion relative to the ground. So we have platform dynamics that arise, and as the platform moves, we get phase deviation on the received signal that could be written out approximately as involving three terms. So we have a phase step component, we have a frequency step component, and we have a frequency ramp component. Actually, a real satellite will have a more complicated set of higher order derivatives that will come out of that will just be modeled best by the orbital mechanics. And it would be, you could write it out in terms of the range as a function of time, and once you have the range as a function of time, that will give rise to all these different derivatives, because you could take the derivatives of the range, the higher order derivatives, and then classify them into phase, frequency, and frequency ramp, and higher. So if we take these three generic types, though, the step, phase step, frequency step, and frequency ramp, we can take that to the S domain, and from the Laplace transform tables, this is what we'd have in the S domain for those three types of phase inputs. And then we could jump over to the final value theorem, like we used before, and take these three possible inputs, play them through the loop error function, to then see what the steady state phase error is going to be as t goes to infinity. And from the final value theorem, that is limit as s goes to 0 when we multiply the quantity of interest by s. So these, what makes this interesting then is we can generalize the loop filters we've been talking about to, in this case, a third order loop. This is a third order loop filter. And then what you can do with this third order loop filter is you can turn on or off different terms. Like if A and B are both equal to 0, then it returns back to the first order loop. If just B is equal to 0, then it's the second order loop we've been dealing with. And if we have B non-zero, then we have a third order loop. And this third order loop is something that you might consider for tracking higher order dynamics like frequency ramps and so on. So if we plug that loop into our G of S equation, so we plug this generic loop F of S into the H of S up above here, and expand it out, or into the G of S, excuse me, plug it into the G of S, this is what that G of S looks like. And then what we can do with that, and this is sketched out in the textbook as well, so I'm not going down this pathway just because I like it, but I do like it because it is relevant, especially when you work in SATCOM, which I do, and some of you will likely also. I guess, Jared, you probably work in it some right now, or at least I know where you're working, you're involved with that. So now we can write an expression all the way down to the bitter end for the steady state phase error in this fashion. And then we can consider possible outcomes depending upon what platform dynamics are present and what sort of scenario we're interested in spending some time on. So I generally go off and do some examples here. There's not really any good example in the book other than a couple of things in this section of the textbook, but this also is a setup for what could be a problem on the exam or the final exam. So the most important thing is just making an assumption about what loop filter is present, and then what sort of static or steady state phase error you might get under a certain type of perturbation that you're going to have on your platform. So for starters, what I'd be inclined to do is, let's just suppose that we've just got a second order loop. Well, yeah, let's just go with a second order loop. So we're going to have B equals 0, but A does not equal 0. And then we're going to assume the only input perturbation we have is the frequency ramp. So we're going to have theta naught equals 0, and we're going to have f delta, which is the frequency ramp, that one equal to 0. But we are going to have a frequency step, is equal to 0. Frequency ramp is going to be not equal to 0. So I can scratch that term, scratch that term. I can scratch that term. So now what I want to do is just take the limit. And the first thing that I would do is do some simplifying here. So it's a limit as something goes to 0, so it shouldn't be that hard of a limit to do. So what we want to do is just take that s and bring it in down below here and just see what happens when we make the simplification. So when the limit as s goes to 0, we're going to have 2 pi r over what? S squared plus kt, and actually I screwed that up. We'll have an s in here, and then we're going to have kt times a. Is everybody following that? I'm dividing one s out of the denominator, so I'll have s squared kts and then kta. But now as that limit goes to 0, as s goes to 0, this is going to be 2 pi r over kt times a. So that what it's telling you is that for a second order loop with a frequency ramp type of platform dynamic, the steady state phase error does not go to 0. It's some number. And so in certain types of platform dynamics, like in a highly elliptical orbit, when the satellite flies overhead, say out here at Schriever, where they have a monitoring station for the AFSCN, there might be a really high platform dynamic as it's whipping around and then flying off again. So there's going to be a large phase error if you're trying to track it with a second order loop. As it comes close, it's going to be building up the error, and then it's going to hit the peak when it flies overhead, and this bounds then the static phase error, or the steady state phase error. If you wanted to be able to track that system without any errors, then you'd have to go to the next higher order loop. On the other hand, if we were to just see what a first order loop would do, if we went with a first order loop, it can't track anything but a phase step with 0 error. So if I was to modify all of this and just sort of start all over again, I'll try to make it go faster this time. I'm going to suppose that we have a first order loop. So first order loop, I'm just going to set those two types of platform dynamics equal to 0, but first order loop, that is gone, that's gone. So we're going to have f delta not equal to 0. And then if we go through and evaluate this limit, we're going to be able to bring an s through the denominator again. We'll have 2 pi, well actually we're going to have an s and an s, so we have two s's up there that we have to bring on through the denominator. So we're going to have 2 pi f delta, pen quit working again, and we're going to have s plus kt, take that limit, it's going to be 2 pi f delta over kt. And we saw this earlier, this is the steady state phase error in a first order loop when a frequency step is applied. If we were to plug in only a phase step, then the steady state phase error would be 0. The loop tracks that without a problem. If we were to put in a frequency ramp, then we're going to have something bad happen. Does anybody want to guess what bad thing happens? It's good if the steady state error goes to 0. It's marginally acceptable if the error goes to a constant, but is still a small constant. But what's the next thing that we would find undesirable? If we have a higher platform dynamic, like a frequency ramp, the steady state phase error is going to not be a constant, it's going to go unbounded. So that means a really bizarre analogy would be if you were on a roller coaster ride and you were worried about getting thrown off the roller coaster and the dynamics was just too much for the roller coaster to handle. What would happen? You'd fly off, and probably wouldn't be a good thing. But so that's kind of what happens here. It cannot hold on. The dynamics is too much for the tracking loop, and it goes off to infinity. So it goes unbounded, which would be unacceptable. The analogy to the roller coaster was just for sort of an extreme example, though. Some of you probably like roller coasters and consider them to be very safe. So, any comments? Okay. So that's just an interesting discussion. Just to understand where tracking loops come in, and tracking loops take different forms, but we have tracking loops for cruise controls too. I think you already, if you ever drive with a cruise control, you've maybe experienced the situation where something extreme happens and the cruise control is programmed for safety to just disconnect. So, like if it's going to try to take you to infinity or something, it'll put the accelerator down all the way, but it won't keep that up forever. And my radar-based cruise control also applies the brakes if it thinks I'm going to get in an accident, but then eventually it just disconnects and it lets me take over after it brakes very, very hard. So control systems can do things like that. The next thing we're going to look at is phase-lock loop frequency synthesizers. This is a more laid-back overview of the synthesizer. So indirect frequency synthesis has been around for many, many years. It's what's responsible for allowing us to have digital tuning on receivers where we just turn a knob or program something in and it will set the frequency of a signal generator. A more contemporary version of what's called indirect synthesis, which is when you use a phase-lock loop, is the direct digital synthesis, or DDS. The generators that we have in the COM lab are DDS types. There are special DDS generators, and I don't know all the ins and outs, but Keysight calls it true form, which is something that's got better characteristics than just a simple direct digital synthesis. But the synthesizer can generate a stable, but yet programmable, my pen is skipping, frequency source. It allows digital tuning in a communications oscillator like an FM receiver in the car or cell phone or you name it device. And it can be used to create a stable frequency source in certain applications. So this is the generic block diagram of indirect synthesis. These days, if you buy a chipset from Analog Devices or Texas Instruments, and both of those vendors are always pushing to the limit in terms of the synthesizers, chips that they produce for the wireless industry. They're a lot more sophisticated than this, but this still has the basic foundational ideas. It's not a sigma delta or fractional n type of synthesizer. This is the predecessor to the more modern types, but understanding this is a very good starting point. So the idea is to have the input to the phase lock loop now be a stable reference. So that's the FREF that we see over here. And so this might be 10 megahertz. That's kind of a common reference frequency that's used. So it might be a 10 megahertz crystal. It might be a temperature stabilized crystal. It might be rubidium standard of some sort. So something that's a very accurate clock frequency. And then you digitally divide that by some integer m, and then you've got the reference frequency into the phase detector of the phase lock loop is FREF over m. And the loop is set up with a VCO loop filter, and then the output of the VCO is the output from the synthesizer, but the frequency comparison that goes on in the phase detector, when you're multiplying one signal times the other, the abstraction in this block diagram is we're just thinking of the loop locks when F out divided by N equals FREF divided by M, because that's the first condition for the phase lock loop to be locked up. If you remember from the phase plane plot, that was the horizontal line passing through 0. That was when d psi dt equaled 0, and that would be the frequency error equals 0 when the loop locks up. So that's all there is to figuring out how the synthesizer works, this simple phase lock loop synthesizer. You just rearrange that equality up there, and you've got F out equaling N over M times FREF. So I'm going to take some examples here, and we're going to see how you can put this into operation and what are the conditions. Like if you're going to be building a tunable oscillator, M would generally be fixed. You would set the reference frequency into the phase detector with that digital divide M, but then you would make the frequency divider in the feedback, and that's this guy over here. I'm going to make that green, but my finger never manages to work properly. That's programmable. So let's just take a simple example, something that many years ago I thought about having a car radio that had a frequency synthesizer in it, because when I grew up they didn't have such things. There was a knob on the front of the radio, and you tuned mechanically a capacitor that would change the frequency of the local oscillator in the super heterodyne receiver. Today it's done with a synthesizer. So here's how you might put something like that together. You want to provide a local oscillator signal for converting FM broadcast band, which runs from 88 to 107.9 megahertz. You want to be able to translate that band down to 10.7. So we have to pick either high side or low side tuning, and we also have to take into account that the minimum channel spacing in FM broadcasting is 200 kilohertz. So two of our side information pieces are, we want to get down to an IF of that. We want to take into account that our channel spacing is 200 kilohertz minimum, and then we have to decide whether we want high side or low side. So in this case we're saying high side tuning. So those three things will give us the ability to spec out the design. And the speccing out of the design is what are the range is for the digital divide N in order to cover the band of receiving 88.1 up to 107.9. So I start right in here by saying if we're going to do high side tuning, we're going to add 10.7 megahertz to the frequency range we want to tune. So we'll be setting our LO at above. So that's 98.8 up to 118.6 megahertz for a local oscillator. The smallest step size that the synthesizer can tune is always the input frequency, which is FREF divided by M. So that says that our reference frequency into the synthesizer, into the phase detector, has to be 200 kilohertz. So if we were starting with 10 megahertz, let's say, we would have to pick a divide value m there. So if we started with 10E6, as in 10 megahertz, and we wanted to get down to 200 kilohertz, would be 200E3. That would say m has to be 50. So we'd need to put a digital divide by 50 in at that point over here if we were starting at 10 megahertz. But in this problem, it doesn't talk about that. It just says what is the reference frequency into the phase lock loop, and that's going to be 200 kilohertz. It can't be larger than that. It could be 100 kilohertz, and then you would take double steps. It could be 50 kilohertz, and then you'd take quadruple steps every time you wanted to change channels. But the most efficient way to go would be 200 kilohertz. Somebody just messaged me, so I'm just seeing who it is. It looks like somebody who's in one of my other classes and never figures out that I'm teaching. He always has a favorite time of writing to me, like right now. I'm definitely not going to be able to respond, but starts making my mind spin how everybody wants to do demos for me. My other two classes, they're doing lab work with the analog discovery, and they're have to demo things to me. So I'll go with 200 kilohertz. Now, the last thing that's in here that I didn't actually work out is what values of n do we need to have. So we need to figure out how that's going to work. So we need to have a local oscillator of 98.8, and divide that by, let's see, 200. See, it's 98.8 E6 divided by 0.2 E6. That's going to be 494. So in order to tune to 98.8 megahertz, we're going to have to set our digital divider, that's the N here, set that to 494, and then to get the upper end, which is the the upper end in this design would be 118.6. So I just have to go 118.6, and that'd be 593. There's a better way though, and a long time ago I would have never even been able to consider this, because when I was first interested in this stuff, I only had TTL logic, and I didn't have logic that would be able to divide a VCO down directly without using some high speed digital logic like emitter coupled logic or something like that. So this would be like, no, you can't do that. But today, I mean, things are much different with the technology we have out there. But so I'm going to look at a mix converter associated with the indirect synthesis technique. So at this point, I segue out, to reduce the maximum divide frequency into the counter. We can use this thing called an offset scheme. And so that looks like this. We take the output of the VCO, feed that into a mixer, which is fed with an offset frequency, and we use that offset frequency along with F out to create a mix frequency, which is going to be the difference frequency. So it's a matter of how you want to work through the math. In this case, I want to just create a difference frequency, so I picked F offset less than F out in this case, and that's a fixed frequency oscillator. And then the math would say if I'm going for the difference frequency, F mix is then going to be F out minus F offset for locking. And so I can put that into my math now to say that F mix gets divided by N, and that gets set equal to F ref divided by M, which is F ref divided by M is our 200 kilohertz. And then I can solve for F out. This is where I know it gets confusing, but F mix and F out are related, right, with F offset. So I can just make a substitution in there is all I'm doing, replacing F mix by F out minus F offset, and then I can solve for F out as N times F ref over M plus F offset. I'm going to let you look at the algebra. It's not stunning math, it's just algebra. So we've used this offset assumption. I'm going to assume that F ref over M is 200 kilohertz. Pick F offset, that oscillator, to be running at 98 megahertz. And then come up with the divide values. So the divide values are much more reasonable. They're 4 and 103 in this case. So not as big a divide ratios are required. There are issues with this though too. This is not perfect. I guess one of the things I would think about myself is if you were building this system, you'd want to make sure that this oscillator at 98 megahertz, which is right in the middle of the FM broadcast band, is well isolated from the receiver itself and does not corrupt anything else in the circuitry, because that would be a frequency that would cause issues. It could desensitize the receiver front end, for example, but we're not really showing that right now. Right now we're just thinking that F out is going to be nice and clean. F offset doesn't get into it in any way, shape, or form, but the reality is a mixer has reverse power flow, so energy will manage to get up this pathway. There's only so much isolation that would be in there, but hopefully you can control the isolation. So I'll let you think about that. You're going to have a problem on the next homework that involves this type of synthesizer with the frequency offset scheme. A couple other applications of phase lock loops would be frequency multiplier. This is, Dr. Zemer talks about this. If you drive the input to the phase detector with a square wave, you can then use the third harmonic of the square wave as the locking frequency. So you have the VCO centered on 3 times the fundamental of the input, so it locks on the third harmonic, and then the output in this case would be a 3x of the input frequency you're locking to. So that's as a frequency multiplier. You could use it as a frequency divider if you put in a pulse train. In this case, the pulse train, you're going to rely on the pulse train's fundamental being at half the desired frequency, and then the second harmonic comes out of the pulse train, and wait a minute. You've got the pulse train is at half the frequency. You lock on to half the frequency with the half frequency VCO, and then the second harmonic of the VCO is filtered to get the fundamental. I think this might be a mistake right here. Low pass filter. No. This is to get FC over 2. So you're getting a dividing action out of this, though. I may have something written down wrong in here. No, I got FC. Yeah, never mind. FC is going in. This is the spectrum of the VCO. That's what was confusing me. So you're dividing. There's obviously other ways of getting that, though. This is a section that's no longer in the book, so we skip over that. A couple other sort of light level discussions are thinking back to double sideband modulation of chapter 3. We were wishing we could get a coherent carrier. Well, with a phase lock loop, we can do that. It's possible to take a double sideband signal of this form, m of t cosine omega ct, and then set up one of two types of phase lock loops, a special loop known as a squaring loop or a Costas loop. So a squaring loop would look like this. So what you do is you square the signal. There's power in that signal, and when you square it, you're going to be sitting at the double frequency term. That's what we're interested in getting. We take the output of our VCO and square it. Send it into a frequency doubler. So we're going to lock onto the doubled VCO frequency. And then the 0 degree phase output from this quadrature hybrid, because remember a loop locks with a 90 degree phase shift, then we use that as a coherent reference, and maybe have to do some phase shift adjustment to get this phase error to 0. Another type of loop that is used in digital communications is the Costas loop. It performs similarly to the squaring loop, except it does it with two arms or two branches, an in phase and a quadrature branch. And it doesn't require the VCO, it doesn't require a doubler. It just is going to use a quadrature hybrid to put out sine and cosine. And then the loop filter is locking with a factor of 2 psi. So it does have two stable lock points because of that 2 psi. And it's often used in the olden days with more analog type digital comm receivers for carrier recovery in a coherent digital modulation scheme known as binary phase shift keying, which is something we'll spend some more time talking about in the next couple of weeks. It is in the project, but it's the lowlier modulation, but it's still bread and butter in SATCOM to use binary phase shift keying. BPSK is just simply a bit stream with some pulses, P, and then the bits are plus and minus amplitude values. So plus and minus ones would be how you translate 0 and 1s to plus and minus 1. And then when you multiply that bit stream, think of bits coming out of a D flip-flop in digital logic with the logic levels adjusted to be plus and minus 1, and then multiply that times a carrier, and then we get 180 degrees of phase shift when the bits change polarity, and this is binary phase shift keying. The way we demodulate digital modulation can be directly at baseband, so we might come in with some setup like this, where we set up a quadrature mixer again, where we bring in a cosine and then split it to 0 and 90 degree versions. We get the components for making what's called an in-phase and quadrature signal, the real and imaginary parts of a complex baseband signal. We're bringing it down to baseband, and then we can digitize it, and then we have the real and imaginary parts in our complex baseband signal, which is this guy right over here. And this is just digital implementations of how you might do a carrier tracking loop. This is for higher order digital modulation, mth power, but if m is equal to 2, this is doing the complete phase lock loop for carrier recovery. The VCO is replaced by an NCO, numerically controlled oscillator. The loop filter is the lead lag filter in the discrete time domain. There's an error generator This is another type which is not a phase lock loop, but I have used it in a design at Atmel, which is now Microchip. This is called a non-data aided feed-forward carrier phase tracking to get coherent carrier. Pretty interesting things. That's about all I'm going to say about phase lock loops. We're done, except you'll be responsible on the exam, obviously. And we'll have another mock quiz on Thursday as well. The next topic, which I thought I'd finish the chapter, but we are pretty close. Let me just prove to you how close we are. A little bit on interference, pre-emphasis, kind of explain what that is, motivate that with an example. Then we have multiplexing, frequency division multiplexing, of which one example is going to be FM stereo, how that works. Quadrature multiplexing, kind of already talked about that a little bit. And then this generic picture, which is no longer in the book, but I put it back in again because I like it. That's it. That's the end of it. So, and because I'm inclined to want to show you how radically different the appendix is going to be, let me just show you what the appendix is entitled and how you can brace yourself for a change of pace. Appendix A, where is it? I have some SATCOM notes there. It's possible that Appendix A is not sitting in here anymore. 1, 2, 3, 4, 5. Alphabetically, it should be at the top, but I don't see it up here. Either that or I'm just not able to see it for whatever reason, but let me just jump back over since I got to get out of here eventually anyway and just let you see Appendix A right here. Physical noise sources. So we'll be looking at modeling thermal noise primarily in receiver front ends, and we'll tour all the way through this and end up with link budgets for radio links. We'll have a application example with antennas in it and effective noise temperatures, noise figures, and things of that sort. It's pretty high level, and it fits well with communications theory, but Professor Song talks about it in her EMAG classes some too. There's an overlap between the different domains. And Dr. Kelker talks about noise figure and analog electronics, high frequency electronics. So it's all good to have different points of view, but I think comm systems engineers should see it from the systems modeling point of view also. So we'll be jumping into this. And this is a nice, easy spin down for the semester. Trust me, you're gonna like this. It just winds down nice and easy. So we're headed for a smooth landing, the way I see it. With that said, and looking at the clock, I'm ready to sign off, but I'll take any questions if anybody wants to bring anything up before I jump back. I'm going to stay sharing for a few moments, but if nobody says anything, I'm going to stop sharing. Okay, I see people have already dropped, which is fine. Well, I'll come in with a quiz next time.